Swayam Prabha. Digital India. Educated India.
In this class on reinforced soil retaining structures, particularly in connection with walls, I will try to explain this example that we covered last time, and further guidelines on the design of reinforced soil walls we will see today. As I just mentioned, we have just discussed this example that we need to construct this in a particular location. You want to construct an 8-meter high retaining wall with a sand backfill. You know, it's 30 degrees is a friction angle, and the bulk density is also known, and we have some surcharge that one can use. You know, the like a traffic loading one needs to consider in some of the many of the designs, and we also know the bearing pressure of the soil. And assuming that we have two geogrids like grid A and grid B, which have design strength of 20 and 40, and then the bond coefficient of the geogrid material is about 0.9, and normally the compacted lift thickness is about 250 mm. So, which means that you have to place this reinforced soil, the reinforcing materials like geogrids at 250 in the multiples of 250 mm spacing, either it could be 500 or 250, right. So, this is what we already seen, that the length of the we first go with the external stability considerations, and we get the length, you know, corresponding to a factor of safety of 2. Say for example, we get this length of about say 6 meters for 8 meters high wall, considering surcharge. You know, surcharge is also there about on all these equations are already discussed earlier, and we also calculate the overturning moment. Then we also check for bearing pressure distribution, and we see that the bearing pressure that is imposed because of the RE wall construction is about 271, and it's less than the bearing pressure of the soil. So, so you can even calculate, actually if you assume trapezoidal distribution, you can calculate maximum and minimum distributions, and we also see that there is no tension developed where the minimum stress is more than 0. So, the other thing is that, as I just mentioned, we have another type of distribution which is called Meyerhof distribution. One can even calculate the maximum pressure as well using that, and that will be much less than this value as well. And this is what I just mentioned. Now, the internal stability, when you are trying to deal with that, we should calculate in terms of the tensile force, and we try to, this is tensile force is given in this expression in terms of the vertical spacing, because the geogrids, they horizontally they are 1 meter length you consider, and you can, based on this, you can get an expression for Ti, you know, the reinforcement force required at any section, any I section, you know, I level. So, one can get this, and then once if PD is the design strength of the geogrid, and you just try to put some sort of simple program in an Excel, you will get depending on the the strength of the grid, like whether it's 20 or 40, one can prepare some sort of results like this. What it means is that you can see here that if you just plot the grids, the spacing versus the depth plot, this is something very useful to see at what level the geogrid A will be working and at what level geogrid B will be useful. Like say for example, if I just say the geogrid A strength, you know, you can see that it is 20 km per meter, and then you need to provide at spacings much less than 0.25, which is not possible. But so you try to go for 40 kilonewton strength, you know, particularly at deeper levels, you have higher pressures. So you need to go for higher strength of the geogrid. So the way that you see is that up to 2.5, you know, up to this level, up to at least 5.5 meters depth, you can go for this grid with this, and subsequently you can use this. That's what it means. Essentially, you can use that in multiples and all that. That's what in terms of the spacing and in terms of the availability of the tensile force. This is what we do. But apart from it, as I just mentioned, we need to go for wedge stability checks, which are, you know, very important. And as I just mentioned, you need to draw some force polygons and get this tensile force required to close the polygon. that I just discussed in the last time. And once you really, even one can do some simple mathematics, simple formulations of minimization and get this equations also. What should be the, the tensile force required to keep a particular wedge. The wedge angle is 45 minus 5 by 2, okay. The wedge angle is 45 minus 5 by 2, and we saw all these expressions, and you get this to ensure the wedge stability. This is one, the total wedge force required to keep that wedge in equilibrium condition. This is what it is. Now, we also have the reinforcement force, at any layer, the pull out resistance is also there. The thing is that there are two issues that we have. One is the tensile strength consideration. The other one is pull out resistance. So, the pull out resistance is beyond the failure zone, like 45 minus 5 by 2 line. Beyond that, you write an expression, and beyond that length, on either side, top and bottom, there is a resistance that gets provided, which is given in terms of this equation, which is like 2 is on either side and 0.9 is that bond coefficient we have seen in the example and all that. And once you have that, you have the passive resistance which holds that, So, this is an equation, and what we do is that we just check for all the wedges, and you try to see that at every level you have this adequate force in the member, from wedge stability as well as pull out resistance. And we select the materials like this. You can see that, say for example, I said A is a 20 kilonewton per meter, and at 1 meter level you have 2 grades, okay, because you have you are providing, why? Because you just make all these calculations from tensile force considerations. Maybe it's just 8 kilonewtons is required. This is without surcharge and with surcharge. You have to calculate 2 things, because particularly pull out resistance is something like, if there is a surcharge, it is somewhat different, and if there is a pull out, if there is a surcharge, it is lesser. So, you have to take lesser values. So, what we do is that, suppose here you get 42, right. So, then pull out resistance available actually, okay, this is whatever is calculated value, right. So, this is more than what is the two material available, right. So, whichever is the least, so that way we try to see that at every level this is maintained, like 42 is more than, if they provide 2 layers, it becomes within 1 meter, right, within 1 meter of the wedge, you are providing two materials. So, it is fine, like you can, the thing is at 0.25 spacing, at 0.75 spacing. In 1 meter wedge, you can provide at 0.25 spacing and at 0.75 spacing. So, it becomes 2 in 1 meter wedge. So, like that you can take 2 meters wedge, and you can see that you will get, particularly here it is alright, but in this case you will get some 141, okay. So, 141 means you need to get the 80, yeah, pull out resistance is higher, right, 141 is higher than 80. So, it is fine, 80 into 4, like that you can check up at every level, and see at any level you are, normally this is like that, the thing is we need higher pull out resistance so that it does not come out. That is how we provide, and tensile force thing is already satisfied here. So, you can see that clearly at every level the pull out resistance is more than the tensile force requirement, and it is fine, it is stable, okay. So, based on this you try to come out with some configuration, like as I just mentioned, with say for example 0.25 spacing, some sort of spacing you can provide, and you can also provide these materials like this, like this is that failure wedge I was telling about, 45 minus 5 by 2, right, all that you can provide and all that. This simple Excel program calculations one can do. Length is also 6 meters. This is a simple structure, right. So, this is in a way simple understanding, but then when you are trying to look at certain guidelines, you should be much more rigorous, and many of these guidelines, particularly Federal Highway, from USA you have BS 8006 we also have Indian Roads Congress provisions to some extent, and there are many codes that we have, even NCMA codes. I just want to highlight you some provisions here, and just this will summarize some things that we already discussed. So, this stress transfer mechanisms, or one is friction, the other one is passive resistance. because of the friction only the reinforcement force is developed, and because of the passive resistance only, that you are able to mobilize this bond resistance and all that. And mode of reinforcement action, maximum it's only a tension. The way that reinforced soil is acting is that it's just only the tension. But then suppose you have a stiffer reinforcement. We have two types of materials. In fact, there are many nowadays. You can even have composite reinforcements also. What it means is that you can have, say I told you the geogrids is an extensible type of reinforcement. Geotextiles is an extensible type of reinforcement. Whereas a steel is not extensible compared to the stiffness that you have in the case of geotextiles, it's much stiffer. So you may call it non-extensible, but then you also have a combination of what is called anchor plates. Sometimes anchor plates also can be provided to reduce the pull-out length. As we saw the example in the case of bearing capacity problem, in which if you only take friction alone, the length of reinforcement will be higher, but the moment provide some sort of bearing which provides passive resistance, the length can be reduced. So sometimes you may even try to provide an anchors and all that. So mode of reinforcement in reinforced soil is essentially tension. That's the main thing. But then if you can also take advantage of shear and bending in stiff reinforcements. Okay, that's that's also useful. Sometimes for example, even confinement action, geocells is one material. So one can do a lot of composite reinforcements one can do. But what it means is that essentially we can understand some of these things in a better way and then design better structures. Then another important test that we need to conduct in most of these tests is that pull-out tests. So pull-out tests are very important. In fact, geogrids, geotextiles, something in the field, you can pull out and see pull out load versus deformation is what you get actually. Then you will be able to assess its long-term performance and short-term performance also. Short-term performance is in terms of its force mobilization, right? The long-term performance, say for example, some materials like particularly geosynthetics, they have a tendency for creep. So because of the creep, there will be changes in the tensile forces and all that. So people may even do the pull-out test maybe after say 5 years or 10 years to see whether the geogrid or geotextile is alright and what is its tensile resistance, what is its pull-out resistance. One can calculate just based on some of this information, right. So they are quite useful. So some more information that we already saw with reference to the example, what should be the factors of safety. Here with respect to MSEW means mechanically stabilized earth walls. Okay, this is a standard terminology that they use. The factor of safety has to be more than 1.5 and then 1.3 in the case of reinforced soil slopes. Okay, then that is for sliding. Eccentricity at the base, like these are all what we didn't discuss this, but in the codes, in some codes it's there. So like the L by 6 is something that we should the middle third rule that we know already, we have to check that, and in codal provisions it's clearly mentioned. Bearing capacity factor of safety should be more than 2.5. Deep seated stability like 1.3. Compound stability like number of failures another so 1.4. Seismic stability, like the factor of safety is can be reduced to 75% provided the earthquake force is considered in the design. That we will see that how do you consider that. Static factor of safety is how much. It's here, it's say for example you have said 1.5 here, then that is without any earthquake force. But if you consider the earthquake force into calculations, you say 0.75 of static factor of safety, and 1.5 to 0.75 will be the value that you should get. So internal stability also, like pull-out resistance, the factor of safety should be minimum 1.5. Internal stability for reinforced slopes about 1.3. Allowable tensile strength, allowable tensile strength of all these materials is something very high, is it not? Like you have we know the yield stress of the steel or geogrids or whatever. So you can see that 0.55 is the allowable stress. Okay. Then for steel grid connected with reinforcement panels, it's 0.45. So this is all in connected with steel, but then suppose you have geogrids, you have a number of reduction factors that I already discussed, and it can go up to about, as I said, because of damage it could be 1.3, because of environmental conditions it could be 1.5. So long term strength requirements and all 1 point, it depends on say 50 years or 100 years, it could be 2.3 like that. If you multiply all of those factors, it may come down to total factor could be 7. Say for example 1.3 into 1.5 into 1.2 like that. If you just multiply, all that correction factors could end up as 7. And suppose the design strength of that material, we got, earlier we used the design strengths of 20 and 40. So 20 into 7, maybe 20 into 7 means 140 kilonewton per meter should be the value of the geogrid or the rating of the geogrid immediately. Now if it has done immediately, you take the sample and test it, and if it shows 140 kilonewton per meter, then it's fine. Then you also have information about all these reduction factors, and use those reduction factors correctly, and then you will get the correct long term strength and all that, and you can say that yes, the design is satisfactory. This is another important figure, like see the estimate of deformations, because reinforced soils are all flexible structures. Like when you compare with the reinforced concrete structures which are rigid, the reinforced soil walls are flexible structures. Because of their flexibility, like essentially because of the interaction between the soil and the backfill, there is some movement, and then what is that movement, how much it can happen is something that one should understand. And see, the thing is delta max is nothing but it is in terms of it's called relative displacement coefficient. They have given here, it's called a relative displacement coefficient, which is again given in the codes, and in the case of inextensible reinforcement is h divided by 250, and in the case of extensible means geogrids, delta r into h divided by 75. So the height of the wall in meters. So for example, if 10 meters is the height of wall, and normally L by H ratio will be in the case of about 0.7 or 0.65 or something like that. Even you have seen the other day, just now 6 meters is the length of the reinforcement, 6 divided by 8 will be 0.75. Like that, normally the code says that it should be about 0.7 H. So when you take it to 0.7 H, this relative factor is about 1, and if you use that 1 here, 1, so this 1 into that H is, say for example, the 10 meters divided by 250. So much of mm will be the or the units of the displacement allowed. Okay, we have seen that we have measured also. Like it's a very important property, because to understand, normally you have to measure deformations in reinforced earth walls. It's very important, and otherwise the problem would be that you will not be able to understand to what extent these relationships are valid. Okay. Of course, this backfill requirements I just mentioned earlier in the factors influencing reinforced soil, but anyhow I will just highlight a few more again. MSE walls, plasticity index should be less than 6, and the gradation characteristics are given like this, like 1 or 2 mm 100%, 0.425, 0 to 60, 0.075, 0 to 15. So more than not the clay 0.075 size, it should be more than 15% all the time. It cannot be less than this, like you can't allow here a bigger number. Okay, it should be in the range of 0 to 15. It cannot be, say for example 25%, which means that it's more like a clay, right? 0.02 is a clay, but then it's also a little finer fraction. So you don't allow them material to be too finer. Okay. Then Cu is the coefficient of uniformity is less than or equal to 4, and for slopes, PL, the slopes it's this is another one. Okay. Some more important, like the backfill material should be free of shale or other soft materials or weak particles or organic matter, because the backfill should not get degraded, or it should not become softening some materials like talc and all that, if you just have a saturation with them, they may become little soft. So, we do not want that. Then light compaction, like the thing is backfill compaction is alright, but when it comes to close to the wall, then you have to have a simple light compaction method, light compactors that you have. One should use them, because what happens if you use the heavy compaction equipment, a lot of stresses come onto the wall, and even the compaction control is difficult. So, they exert additional stresses. So, best is to have a light compaction equipment, and also good backfill in terms of the friction and drainage, like sometimes very good material they use next to the backfill and the wall facings, and then the backfill should be compacted to 95% density, bulk density, and 2% of the plus or minus 2% of the moisture content, like standard Proctor, right. And peak shear strength parameters should be used, like you try to take the sample, reinforced soil, you are trying to use it as a material there for wall fill, you try to do a direct shear test or a triaxial test, and then get the peak shear stress parameters, residual stress parameters. What it means here is that they recommend that you should take peak stress parameters. Then a minimum friction angle of 34 should be obtained actually, okay. It can't be less than this, that's what, that's some of the specifications even in IRC we have. And some of the backfill materials, one should be careful that they are not liable for corrosion effects. So, what we should do is that you should find out the electrochemical properties of the backfills, particularly when you are using steel reinforcement. So, you have some the parameters like resistivity, pH, chlorides, sulfates and organic content. You have permissible limits here. So, one should just and then you have a standard method, ASTO methods one can use, and you have to see that in this particular backfill or the wall fill that you are using, you don't have, you have the properties less than this limit specified, particularly when steel reinforcement is present. And there are some cases, people also provide coatings for the reinforcement, and in fact, the other way is that people also provide corrosion, allowances, like you should be able to know what are the rates of corrosion in a particular environment. Say for example, if the pH is this much, what is the corrosion rate, So, one should be able to see that, and these rates of corrosion and allowances that you need to provide, or the thicknesses you need to provide, are specified in codes, okay, that you should see. For example, BS 8006 code, it is very good. So, it gives information. So, this is about reinforced soil wall fill, okay. But there is some material that is next to the retaining wall, which is called retained fill, So, that retained fill, next to that, if it is weak, then again there is a problem, whole material should collapse, it can collapse, right. So, you need to be very, even the foundation soil, retaining RE wall is fine, but the backfill or the, backfill means next to the retaining wall and the foundation soil have to be really good, then only the whole structure stands. So, you need to see that the properties of the retained backfill or the retained fill as well as even the foundation soil are reasonably satisfactory, and so you should go for standard testing, standard testing of all these materials and the position of water table. Say for example, you are constructing a wall here next to some slope, and you need to know what are the drainage channels that are likely to be intersected, so that you can provide proper drainage in the RE wall. So, these are all required from global stability point of view. Then, when you are trying to study that behavior and dynamic conditions, what is going to happen? During an earthquake, the retained fill exerts a dynamic horizontal force, like its PAE, like the active earth pressure due to earth pressure, earthquake on the MSE wall. And in addition to the static test, already the horizontal force is there, and when earthquake comes, there is a horizontal force that gets created, and the reinforced soil is also subjected to a horizontal inertial force, like we say PIR, which is nothing but MAM is a mass of the soil and its acceleration, right. How much is that force that it gets subjected to? So, these forces you should know, and the active portion of the reinforced soil is assumed to act at a base width of 0.5 h, and AM is the maximum horizontal acceleration in the reinforced soil wall. So, what we do is that we calculate these forces like active force due to earthquake and also the horizontal inertial force due to in the reinforced soil mass, and add. So, then actually the force PIE you can evaluate by Mononobe-Okabe method. I am sure that you must have learned this procedure in earthquake geotechnical engineering, where you get some information about how much is the, if you know the horizontal force or the horizontal earthquake coefficient, you can calculate the earthquake force acting. Okay, that earthquake force should be added to the static forces, and including all static means weight, surcharge and all that, and then the dynamic stability is evaluated. Allowance of about 75% of the static factor of safety is allowed. Okay, that is what we discussed already. This is the way it is like this, like as I just mentioned, and we take that this much of 0.5 h, this is a mass that gets subjected to dynamic force, and this is center of the dynamic mass, and mass for inertial force. How to calculate inertial force? This much of soil participates in the movement. So, PIR, this is the one, and this is what you calculate like this. Okay. Then we assume that we take 50% of the AE and it acts at a point 0.6 h. The static force acts as h by 3. So, these are all some, when you are trying to calculate what are the things you have to calculate: sliding forces, factor of safety with respect to sliding and overturning, right? You have to calculate when you are looking at, and then all that calculations you should make, even the bearing capacity check and all that. So, this is very important when you are trying to assess the stability of the reinforced soil under earthquake conditions. So, of course, the codes give much more detailed matter, and then you have software as well, but one should be very careful in understanding these provisions properly and then applying some of these rules. Okay. So, suppose the material is subjected the reinforced soil wall is located in some area where we know the horizontal ground acceleration based on design earthquake, and so we calculate the maximum horizontal acceleration. AM is in terms of 1.45 minus A into A. Actually, you know about amplification factors in earthquake that comes based on this. There is a lot of research done on this, but this is the way that it is given in the Federal Highway Code. So, then the PIR and the PIE is given by these expressions like 0.5 AM gamma R, means reinforced soil, and then h square, and then 0.375 AM into gamma F fill h square. So, you add to the static force acting on the structure 50% of the seismic force and the full inertial force, as both forces do not act simultaneously. So, as I just mentioned, we just follow this particular diagram what we discussed, and then calculate all the forces and see if the materials or the factors of safety are acceptable. A few more additional points that we should understand. If this is a wall structure like this, and there is a this slope angle beta, like in the case of particularly in embankments to get this particular condition, you should be able to know how to calculate the maximum tension force and all that. In the case of extensible reinforcements, this is a simple for an illustration only. You have a lot of guidelines on this, particularly Federal Highway. It's full of illustrative examples and calculations. This is a typical diagram in which, say for example, you have to calculate a H1. H1 is you have to calculate like this. Suppose there is a, you have an RE wall like this, and then there is a 1:2 slope maybe, and then there is a road here, and then all that. How do you do that in the case of, how do you design? So, how do you take the active force, active thrust or the active zone? So, that H1, what is the height you have to take? Sometimes, most of the time the question is that there is a fill here. How do you take the height so that you can go ahead with the design? So, H1 is H plus this tan beta into 0.3 H divided by 1 minus 0.3 tan beta. So, that H1 will be the height, and so that's how the classification of these zones, all that would be done. This particular thing where this is to be divided, it's H1 by 2 and H1 by 2, and this is how it is done. And this is in the case of steel reinforcement, please remember that. Okay. Then this is the active zone, this is the resisting zone, right. So, these are some guidelines on how to do that. And when you have extensible reinforcement, you have a line like this, which is like 45 minus 5 by 2 line, beta is different. So, in this case, it is just the H, and the zone of in the previous case, the zone of maximum tension is like this. Okay. In this case, it's like this. Okay. And suppose there is a surcharge, PV, some load, concentrated load at some at the top of the road. How do you take it? It's also that's given, like say for example, there is some load here, footing load, and then there is an RE wall you have to construct. So, how do you take these forces? It's given here. If there is a load here, it has a 1:2 distribution, which is common in soil mechanics, and for isolated strip load and for all these loading conditions, they are given. And once you know this, you can calculate the the stress. This actually the thing is, if you have a reinforcement here, it will have maximum stress, right. And then if you put a reinforcement here, there is a distribution. So, how much of force is coming, like given that you have an area, say for example, BF is a footing foundation, BF into L, then the load PV divided by BF into L will be the total stress acting at this point. Now, you want to reduce that length. So, you have to proportionally reduce using this 1:2 distribution, and then design the reinforcement properly. Okay. You have to design the reinforcement properly, and the thing is that just we saw that it's Ka times sigma V, right. How do you calculate the tensile force in the reinforcement? Essentially, what is the horizontal stress? How do you calculate? You are calculating the tensile force, and it's over some spacing, and say you need to essentially calculate horizontal stress. So, horizontal stress is always a fraction of or the multiple of vertical stress. So, when you have a surcharge here, and you need to have this vertical stress and multiply by K0 or Ka, whatever, right. Then you will get the horizontal stress, and then knowing the horizontal stress, you can design for tensile force required. There is another case where your RE wall is on a curvature. Okay. So, there could be some horizontal force acting like this. What you saw was a vertical load, and even for horizontal force also one can completely check this. Okay. And they have some appropriate formula for this. What should be the lateral force that one can expect when you have a thing like this. So, that is also possible. So, and then you also have similar guidelines. The thing is that they are all given in some codes. Just one should be aware that yes, it is possible to follow these codes and then give some design solutions. And then they are all very important. You can't ignore them. That's very important thing is that you cannot ignore these factors, and you should consider them in design. So, what we do is that we calculate the additional horizontal stresses due to earthquake to be calculated, and even any loading, and then tensile force need to be evaluated. That is very important. So that whatever I just said, you can calculate a proper geogrid, arrive at a proper geogrid specification. What is its tensile strength? Or like say we have seen that in the design calculations just we discussed, we saw that the tensile force is 1, and then we also have pull out resistance is 1. You can repeat all the calculations, assuming that you can even back calculate certain designs and see if the things are all right. Then connection strength. Very important point is that when an earthquake comes, or even in the simple case, we connect the reinforcement to facing using some connections. If the connections are not good, there is a possibility that it can go very badly. Like, all specifications of backfill, compaction, everything is perfect, but if the connection strength is poor, like, I saw a case, it's available close to Bangalore, where the long time back, the connection, was so weak that it came out, and all the facing panels just came out. They are all on the ground. So that's a very poor situation. Reinforced soil, the geogrids are all intact, but since the connection was not good, it couldn't hold the facing weight. Just all the facings came out, and people have to rehabilitate that whole RE wall using soil nailing. Okay. So I'll give a small example. This is that facing, and you have a some sort of connections here, many of them, and there are people have different connections, different types. So one should, and actually code says that suppose you are trying to make a connection, 60% of the tensile force should be taken for design. So your connection should be designed such that it can take care of the even facing also. So say it comes on the facing, but connection needs to be properly done. That's one thing. So the other important thing that I would like to highlight is that in the case of a precast panels, you have to do this. In fact, I saw 1 or 2 failures on these lines where the connection was not good enough, and it yielded. Okay. And the second thing was, as I was mentioning about segmental wall construction, right? You have a number of blocks like this, 1, 2, 3, 4 like this. Okay. And when you have this type of materials, they have to be properly locked. Actually, they have to be, there is a setback and all that was given, but there is a procedure that one needs to follow. Otherwise, the equilibrium of each block and the forces and the anchorage and all needs to. Otherwise, there is a possibility of total collapse that could occur, that we saw in failure mechanisms also. So what I want to say is that reinforced soil technique is something very viable, and has been very useful technique in many countries, and it contributed to infrastructure in significantly. It increases the speed of construction. It is very useful to construct. The speed of construction is very fast. Of course, it's economical, and aesthetics, it's wonderful actually. Compared to many of the treatments for the retaining walls that you have, using this precast panels or segmental wall construction, you can bring in a lot of nice finishes to the retaining structures. Very importantly, one should understand that this technology needs to be understood in terms of its response, construction features. The RE wall is actually a construction technology. The way it is constructed in the field is very important, and I have seen many cases where the specifications are all right, but if it's not done well in the construction, the way you join, the way you erect, the way you place, the time of placement also, like if you don't allow full drainage to take place, say normally everything is outside only. So if the lot of rains are there, and if there is still some drainage didn't occur, you start constructing, then it becomes problem. So there are many issues that one needs to understand and take care. So because it's essentially construction. So as I said, a failure of RE walls have also been noted in a few places due to lack of understanding of the behavior of RE walls, because people feel that it's a somewhat easier system, but technically yes, it's a very nice and elegant technique, but the implementation needs to be a little more careful, and of course guidelines are excellent in this, and one needs to understand them properly. And as I said, Federal Highway guidelines are there, NCMA guidelines are there. They need to be studied in detail for many of the installations. Even for seismic stability and deformation, there is a lot of scope for research also on these lines, like as I said, 0.75 times a factor of safety, and so many issues that are deformations, and many issues are there. One can investigate in a very, very comprehensive manner and identify new research insights, insights into the behavior in a comfortable manner. Thank you.